Hello, my name is Lachlan Miller. I was a 2023-2024 Pawsey Summer Intern, and in this video I'll be explaining what I did over my internship project to implement shear flow for ab initio molecular dynamic simulations. So, what is shear flow? Shear stress occurs when a force is applied parallel to the surface of a material, creating a deformation or shear flow in the direction of the stress. Here, what I've got is the slot equations of motion, and so when we're performing a molecular dynamics simulation, we update the position and the momentum of each particle at each time step. These values are interdependent on one another, and as you can see, what I've put in the green boxes is we don't just have the position and momentum values, we also have a grad U term. For elongational flow, this grad U term is simply a strain rate in the direction of the shear stress, and that is the amount that we want the particles to be moving or flowing in that direction. I've got a video here which shows a box of argon undergoing shear stress, and as you can see, the particles at the top of the box are moving further to the right than the particles at the bottom of the box because there's a different degree of shear stress at the top of the box compared to at the bottom of the box. So we've already been able to model this with a classical force field, but we want to be able to extend this to ab initio molecular dynamics. And ab initio molecular dynamics is where the forces between the atoms, so the attractive and repulsive forces which determine how much they want to move apart or towards each other, are recalculated at each time step dependent on where the atoms are with respect to each other, and that uses DFT, so the assumption that the electrons move around the atoms in response to their environment. And this enables us to model chemical reactions and polarization effects. So in a water molecule, for example, the electrons aren't going to always be in the same place around the water molecule, and it will depend on where the molecule is. So as you can see on this diagram, there's an electrolyte salt ion in the middle, and the electrons are going to move around in response to that. CP2K is the software that I made modifications to because CP2K allows us to perform these ab initio simulations. I used Git was a really handy software to save my changes as commits and revert to previous commits if I accidentally made a mistake. I used Vim as my main text editor, and I used a little bit of GDB and Valgrind for debugging and working out what CP2K was doing in order to make the modifications and implement the slot equations of motion in there. Output from the system, so the conserved quantity was the same as the energy that we expected based on the shear stress that we put into the system. And as you can see here, this is for that same box of argon that I showed earlier. The analytical and conserved quantities of energy overlap exactly, demonstrating that the slot equations of motion were implemented correctly in CP2K for the classical simulation. I used Pawsey's Cytonix supercomputer to run some larger scale simulations and to start doing those ab initio simulations where the forces are recalculated every time step, so they're a lot more computationally involved. And I got a very good agreement between the viscosity calculated from my simulations using the slot equations of motion and the expected viscosity. So as you can see from the graph on the right, the viscosity that I output from the linear regime at a strain rate of 0, so at equilibrium, is 2.5 by 10 to the negative 4 Pascal seconds, and that's what we expected. In the future, we're going to do more testing with ab initio calculations, and it appears to be mostly working, but we need to iron out a small bug related to the interaction between force calculation and the box deformation that gets more complex with those ab initio force calculations. This also has applications for working with ionic liquids, modeling reactivity in a solution, and a whole bunch of exciting applications with systems undergoing shear flow. Thank you to AIBN and CGCMS and my supervisors for their support.